So we're looking at 4 ultimate limit states considered. First of all, we've got a short-term bearing capacity failure of the foundation, the short-term sliding of the foundation, then the long-term bearing capacity and the long-term sliding capacity. Again, we're not considering earthquakes here, but you could do if you add the loading and modify the geotechnical parameters and the strength reduction factors to take into account earthquake loading. So once again, we put in our input data, the breadth, width, length, thickness of the foundations. In this case, it's 2 meters wide and 3 meters long. The difference here is we're applying our load eccentrically, so it's not in the middle of the foundation. And we've got designed vertical loads and horizontal loads, significant loads in both directions. And we're also applying moments. Now our soil parameters, we've got 2 lots of soil parameters. We've got our short-term values, so we've taken SU, which you should get from your geotechnical engineer. SU is 75, and the unit weight of the clay is 18. And then in the long term, we're looking at the effective stress cohesion as 12.5, and the effective angle of shearing resistance as 25. Again, we work out our coefficient of passive earth pressure. In this case, it's 2.4. We've also got sand, so we've got backfill over our pad foundation, and we can add the parameters for that. What we're really looking for is the unit weight, because we're just concerned about the dead load applied. Here is our effective area diagram again, and how we work it out. So on the left, we have the plan showing the effective area, and on the right, we have a calculation for the eccentricity. So in this case, you're looking at a cross section through the foundation. Here is our resultant upward force. Here is the applied moment, and here is the eccentricity from the position of the applied load. We take our strength reduction factors as before from the code, and we work out the total stress in the ground at the underside of the foundation. We derive our design loadings, so we've got our weight of the foundation, the weight of the backfill. With that, you can add that to the applied vertical load to get a total vertical reaction of 374 kilonewtons. Taking moments about the point of loading, you then work out what the eccentricity is about breadth as 125 millimeters and about the length as 139 millimeters using these equations. And these are given in the code, which then gives you your effective length of the foundation as 2.27 meters. It also gives you the effective width of the foundation as 1.749 meters. And in both cases, we can check whether the eccentricity has meant that the resultant load is still within the middle third. So we've got a relatively balanced foundation. And if it isn't, you need to redesign your foundation dimensions to suit. Our first ultimate limit state check is on the short-term static foundation bearing failure. So we've got a design bearing pressure of 94 kPa. Now the code gives us a bearing strength factor NC of 5.14 because our effective angle of shearing resistance is 0. We can work out the rest given that as NQ and N gamma as 1 and 0. We've got our shape factors, and we've got our ground inclination factors. We've got horizontal ground, therefore they're all 1. We've got our depth factors, and again we check, depending on the ratio of the depth to width, which factor to take. And then we've got our ultimate bearing strength as QU as 504 kPa. So our design bearing strength is 227. It's bigger than the applied, so we've got a utilization ratio that's fine. Going on to our second check, which is our short-term static foundation sliding failure. So this is a similar approach to before. We're just looking at the adhesion effectively underneath the pad foundation and multiplying it by the area. We also add the passive resistance in both directions. And again, this is the adhesion multiplied by the thickness divided by the length. And then you've got your resistance given by B1VM4. Again, if you want to be conservative, take that out in both cases and see if you're still okay. And so our design sliding strength is 300 in the width and 286 in the length. So our capacity divided by our load is well over 3, so we're good to go. Our third check is on the long-term static foundation bearing failure. Again, we work out what effective vertical force is. And this time we take into account the pore water pressure underneath. And we work out what our eccentricities are again, because our effective vertical force is different, which gives us an effective length of 2.29 and effective width of 1.73. So these are slightly different from the short-term values because we're now taking into account pore water pressure. Now, because the depth of the groundwater isn't particularly deep, the figures are not hugely different. However, if you are a much deeper foundation with a much greater height of groundwater, then there can be a big difference. And if it's deep enough, you might even get uplift from buoyancy. So we check whether our effective width and our effective lengths are within the middle third. We found that they're good, and derive our effective foundation area and our design bearing pressure based upon the resultant force divided by the effective area. Here are our recalculated bearing capacity factors. Now that we're looking at an angle of shearing resistance, and we work out the shape factors again, work out the ground inclination factors are still 1, and our depth factors are worked out using those values. Again, rework out what the load inclination factors are, because we've got different values for our reaction and different values for our effective areas. And we put it into the very long equation again and work out that our ultimate bearing strength is 382, so our design bearing strength is 171.9, so it's significantly higher than the applied bearing strength, so we're okay. And the fourth and final check we do for today is the long-term foundation sliding resistance. And so our sliding resistance at the base is again the cohesion underneath plus the friction generated from the vertical reaction. We look at the passive resistance on the footing face and calculate it as normal. And if you want to be conservative, take that value out there, which has been borrowed from B1VM for the previous edition. It makes a little bit of difference, but usually not enough to put you over the edge. So it reduces our factors of safety in this case. So our total design sliding strength is 172, and our sliding strength in the long direction is 172 as well. So our factors there are going to be 2.2 in both cases. So that was the Mathcad.